Swayam Prabha. Digital India. Educated India.
Welcome to the lecture 7 of numerical ship and offshore hydrodynamics. Now, today we are going to discuss this following topic, that we are going to discuss the uncoupled heap, pitch and roll motion, and also after that we are going to discuss the coupled equation of motion, where you get to know about this mode J and K, etc. And after that we are going to discuss something about the fruit scaling if time permit, or otherwise we can continue the next lecture. Now, before we start this discussion on heap, let us continue from our last lecture, where we are going to discuss about how I get the radiation force from the experiment, right. And if you remember that we are actually end up getting a relation A equals to 1 upon omega square multiplied by C minus F A by xi A into cos epsilon and then minus m into omega square, and then you get the expression for B, the damping, is equal to 1 upon omega multiplied by F A divided by xi A into sin epsilon. Now, here that time in the last moment we did not discuss how to get the cos omega and sin omega. There is a many way of getting it. Now, if you look at this expression, this F A is basically that you are getting from the signal from experiment, xi is your input, right. M mass is, you know, that the restricting between C, you know, and omega also of course your input. So, only thing is that you do not know the phase epsilon. Now, how to get the epsilon? That from the machine you know the record of the forcing function. So, this one is the, let us say, forcing function, and again that the response also, that force that you are getting from the device, let us say it has this one, right. Now, if you do the simple FFT, you will get the phase, otherwise you know you need to integrate in averaging the time period, and then you know that this how to get this phase numerically, like mostly we are going to do the FFT. Otherwise, there is another way of doing it, but nowadays you know, like you know this, then you need to integrating A and B in order to get this, you know, the sin epsilon and cos epsilon, but best way to do that, you have two signal, do the FFT, get the phase. Okay. So, this is we are going to discuss from the last class. Now, today we are going to start a new topic. We need to discuss the three uncoupled mode. It is heap, then pitch and roll. I discussed pitch first, before the roll. Okay. Now, in heap the uncoupled equation of motion is m plus A. Now, I am not using A33, you can use A33, okay, if you want, or okay, let us make it m plus A33 into x double dot 3 plus B into x dot 33. Now, C is nothing but here rho G into AWP, the water plane area, into x is equal to your the forcing function F. So, now here you know the natural frequency for the heap, that is omega z normally called, because it is about the heap, see about the z direction. So, we can write W3 also if you want. This equals to square root of rho g AWP divided by m plus A33. Right. Now, here definitely in this numerical ship hydrodynamic class, we are going to discuss how we are getting this heave added mass A33. Now, suppose however, in first shot if you ask somebody like how to estimate the natural frequency for heave. Right. Now, AWP is a geometry property, of course, you know that rho is the density, g is g, you know the you can approximate 10 or 9.81 whatever. M, you know the mass. The only thing it is coming from the hydrodynamic side is basically the term A33. Now, ideally speaking for engineers like to get a realistic estimation how to go about it. Now, if you know that how we get the radiation force, this is as follows, like we did for the experiment of the same thing. We have this we have this vessel and then we oscillate this vessel in calm water, and then that corresponding pressure if you integrate you will get the radiation force. Now, if you see that essentially you can think of this ship basically pushing the water surrounded by this body, and because of that you can assume that that pressure get created. So, therefore, now you can think of let us say a rectangular barge, right, and suppose I am pushing it downwards, I am pushing it downwards, okay, and then I push forward. So, can you tell me that you know from your basic idea, like if you push this body downwards, right, like if I have this mobile with me, if I push it downwards I will push more water, or if I push this way I push more water. I know the answer is, you know the answer is basically if you push downwards they are definitely you are going to push more volume of the water, right. Now, having said that, if I that it means that added mass in heave direction definitely more than the added mass in surge direction, like this is how I mean we could approximate, like because we are in heave mode we are pushing more water compared to the surge. So, therefore, in A33 normally we approximate some 70% to 90% of the mass of the body. Okay. So, this is how actually you can approximate the added mass of the body, fine. Now, let us take another thing, very interesting thing. Now, let me write the time period, of course, I mean it is the opposite 2 pi square root of m plus added mass A divided by into rho g into AWP. Now, what I am trying to say is like let us now we assume that A let us say some 90% of the mass. Okay. So, then I can redefine this, now I can call T z the time period in heave, which is 2 pi square root of let us take 1.9 into m divided by rho g into AWP. Now, here you can see that mass is constant, rho you know this what rho of water, sea water, g is constant, pi is constant. So, I can very easily see T z varies as 1 upon AWP. That means in ship, now if I look at the from the top, so it is the top part of the ship or the barge. Okay. Now, if you increase the area of the barge, right, then basically your natural time period basically decreasing, right. Now, if you increase if you decrease the barge, this natural time period will increase, and if you increase the water plane area your natural time period will be decrease. Now, you see there is a totally different from the hydrostatic thing, like I will tell you the fun. Here you increase this, then natural time period will decrease. Now, let us say in normal situation, suppose you have this barge little bit slender, and then you can what you say that if it is slender, then you can that natural time period T z becomes some let us say 10 second or something like this, let us say like this. Then but you are not happy, because if your ship becomes slender, right, then you are fearing that it might not be hydrostatically stable, because the restoring moment may be less, because what you did to make it slender, you compromise with the beam of the ship. So, it means that your beam of the ship is smaller, right. So, in that case you are having some kind of scarcity, like your the ship may be capsized with this beam. However, you are getting very nice natural time period of 10 or 15 seconds, something like this, right. Now, if you want to compromise with this, so and you want to put more importance to the stability of the ship, and if you increase this now water train area more, so definitely it comes down to the now 5 second, something like this. Now, what is happening now, what is the difference between these two? When it is 10 second, then actually if you are on board, you can have little bit easier way of going inside the ship, because ship naturally moving very slowly with its natural frequency 10 second or 15 seconds, something like this. However, you are thinking your ship is not stable hydrostatically, and now what is happening, it is now at 5 second, your ship may be now more stable, but your natural period become increased. So, therefore, you might feel uncomfortable while you are boarding on the ship. Now, see, in one sense if you compromising on the comfort of the person, so your ship might be stable more, and if you are thinking about the comfort of the passenger, maybe you have to think about the stability, how stability is, and you have to look out the. So, that is why design become very crucial, or I mean very interesting in this such situation, because it is so counterintuitive, like I am looking for the comfort of the passenger, I am compromising on the stability of the ship. On the other time, I try to make the ship will be very stable, increasing the beam, and then because you have limitation of the length, of course, like you can't make it 300 400 meter long to increase the water train area, something like you can't, and that does not help also, because your this momentum is not changed. So, anyways, so therefore, these are something very interesting thing, like while especially for the engineers, like who is going to design a vessel, inland vessel or something like this, and some passengers going there, some ro-ro, sea-ro, pack-ship, that time they have to think very logical way how to go with this. Okay. Now, coming to the pitch. Now, I am just now the equation of motion is same. Now, I am just talking about that natural frequency. Now, you can call this omega theta, right, and this is equals to m plus, now it is a 55. Oh, sorry, it is not natural period. Okay, just a second. Now, you can call this omega 5, or you can call omega theta. This equal to square root of rho g v into g m l divided by m plus a 55, right. Now, here also that how I approximate a 55. So, now we can have the radius of gyration k y y. So, then we can think of this, we can again rewrite rho g v into g m l divided by m plus m into k y y square, right. Now, here also as you know that again I am trying to get some percentage of m, right. So, here also let us take again pitch also displace of course it displaces more water compared to the roll of course. So, you can take some again some 70% or 60% of the m. So, then we can approximate this as rho g v g m t divided by let us say 1.6 into k y y square. So, that may be the natural time period frequency. Now, on the natural time period then t theta or you can say t theta or you can say the t 5, this equals to 2 pi multiplied by 1.6 into k square y y divided by rho g delta into g m t g m l. Not L, sorry. Now, here also you can see my T z T theta is varies with 1 upon square root of g m l, same thing. But now, this g m l is so high you really do not have to compromise much on this, because it does not affect the design as such, right. But in case of a roll definitely it is going to affect. Now, let us see what happened for the roll. Now, in case of a roll, that your natural time period that you can say W 5 or W 4, this equals to again rho g v into g m t divided by again it is, now it is m 4 for like, and also it is A 4 4. Now, here again the same thing, if you again do all these things and now you really actually this is much lesser compared to the pitch, because here you can see only you have this thing, right, and now if it is rolls like it really does not displace much water as such, right. So, therefore, this could be taken as let us say maybe some 2.5% of the whole the mass of the body. Okay. So, now again you can again approximate this as, now here it is just is a very crude approximation. Okay. This we are definitely going to get from our that hydrodynamics that we are going to discuss in from the next week. Okay. But here it is just very quickly I try to estimate what is the value, right. So, then again if you do this everything, then you can just substitute everything here. Okay, I missed it is let us say 1.25 into k x x square into m, something like this. Okay. So, also you can find out that time period T 4, it is again it will be varies is 1 upon square root of g m t, right, fine. So, then we understand from these three, for the heave mode the T 3 is varies over 1 upon square root of water plane area, then your T 5 varies with 1 upon square root of g m l, and then T 4 varies with 1 upon square root of g m t. Now, what I am trying to say is as follows. Now, g m l is much higher, is the order of length, right, and then you can see the water plane area also you can let us take a rectangular bird, it is also L into B, right, something like this. So, this two is actually these are fall in more or less same range. Okay. However, you can see that GMT is much lesser compared to all these values. So, therefore, comparison to the heave natural time period, which is normally 5 to 15 second. The roll natural period actually much higher, it is something around let us say 12 to 20 seconds, something like this, or on an average let us say 15 seconds. So, idea is it is much higher than this. Now, why this is severe? Because in day to day life that we are traveling in ocean and all, that most common waves are having this time period. I mean they are mostly from 10 second to 20 second. So, this is the range of the the time period of the ocean waves. Now, so you can see that it is very much possible that roll natural time period falls within the range of the this so called regular waves. So, therefore, in ocean we have to be very careful about the capsizing of the vessel, especially we have to take care about the roll, and also actually because of this we have huge discomfort to the passenger also, because sometimes if we start oscillating in some resonating mode, some waves hitting here is close to the natural time period of the roll, then the passenger having lot of uncomfortable situation. Some people vomit also, you can call this sea sickness, right. Okay. So, this is more or less that is what I am going to discuss today about the heave, pitch and roll. And now, let us start something on the coupled equation of motion. Now, again I am going to say you that like here this one more concept is the encounter frequency, and we are not discussing here right now. When we discuss about the forward speed problem, that time again we come back and we discuss something on the encounter frequency. Here we assume that vessel does not move forward, it is floating. Okay. Now, in coupled equation of motion, if you remember that we are using here k is equal to 1 to 6 m j k a j k x double dot k plus b j k x dot k plus c j k into x k is equal to f of j. Now, here what is j, what is k? Now, j is basically the mode, j refers the mode at which the ship got excited. Okay. Now, that is why it is a right hand side, fine. And then k basically that because of this happened, then what affect in the other mode also. Now, let us give an example. Now, suppose you have a box and then you start oscillating in this mode 3. Okay. Now, tell me one thing, even if you oscillate in mode 3, right, still you can get some moment in direction of pitch. Is it possible, right? That means, if I am oscillating in heave mode, like again taking it, if I oscillate in heave mode, so there is a possibility definitely I can get the force in this direction also, right. Now therefore, now if it does not happen, then definitely there is no coupling. But however, in most of the situation that many modes are coupled to each other. That means, for example, heave and pitch definitely coupled to each other. So, if I do this exercise, definitely I can get some force like this. And similarly, if I oscillate the body in this direction, definitely I can get some force along the heave direction. And so, this is what we are talking about. I am always looking for the force along jth direction in the left hand side also, because this is my exciting force, right. So, we have to match the dimensions. So, therefore, if it is a heave force, so then the left hand side everything should be heave. But however, I can get the force in the direction of heave, however, I oscillate the body in maybe the direction of pitch, there must be some component along the heave, right. Even I do something sway, still I can get some component along the heave. For example, I am assuming if I oscillate in roll, I can expect some component along the heave, right. So, that is what is all about my K mode. Okay. Now see, if you write in this as a matrix form, so definitely you can see that it should be something like this. You can have this M is a 6 cross 6 matrix, right, with respect to this x double dot, and also you can have the matrix A also 6 cross 6 matrix, right, and with this again x double dot, right, and then you can have all this B also the 6 cross 6 matrix, this also 6 cross 6 matrix, and then of course, is for the engineer, right. Now, thing is that not all are coupled, right. For example, like if you consider the coupling, normally that is this heave is coupled with pitch, that is this is the most we do that, and roll we can consider that uncoupled, but however, roll is coupled with sway mostly, right. So, now if you write the equation of motion, normally most of the softwares what they do is they write the coupled heave and pitch equation of motion, and they write the roll single degree of freedom equation of motion. Somebody also coupled the roll with sway, especially for the strip theory and all. Okay. So, let me write now that coupled heave pitch equation. Okay. Now, in that case, in the right hand side it should be only 3 and 5, right, and then here I am now just here I am just writing M j k plus A j k into x double dot j plus, okay, this should be like B j k x dot j plus C j k x k equal to f of j. Now, here j also 3 and 5. Now, let us take j equal to 3. So, right hand side throughout it is f 3. Now, let us write the left hand side. Now, it should be m 33, which is basically the mass of the body, plus a 33 into x double dot 3 plus b 33 into x dot 3 plus c 33 into x 3. Now, plus I am talking about the 5. So, here you can see that j should be 3, but now I run k for 5, but m, so there, but m 3 5 is 0. So, I do not take this. So, I have a 3 5 x double dot 5 plus b 3 5 x dot 5 plus c 3 5 x 5. Now, you see that what are the second component? Second component is this, like if I oscillate the body in the modes fifth mode, that in the direction of the pitch, then what is the component of the force along heave direction. Now, you see that this equation all is, it is not possible if I solve it solely. I have to take the another equation, right, because to compute this term, that x double dot 5, x dot 5 and x 5, I need to have another equation which is I 5 plus a 5 into x double dot 5 plus b 5 into x dot 5 plus c 5 into x 5 plus now a 3 into x double dot 3 plus b 3 into x dot 3 plus c 3 into x 3 is equal to f 5. Now, you can extend this for your all 6 degrees of equation of motion, right, and you can get that many term is 0, many term is non-zero. Again we are going to discuss these things, again we discuss later on when we dealing with the hydrodynamics, getting all the coefficient and going to solve this equation, definitely we are going to discuss this. But right now let us stop here today. Thank you very much.